the equilateral triangle. Then we have basically three types of symmetry here. The first type is rotational symmetry, which you can rotate the triangle by 120 degrees to 104 or to 140 degrees clockwise, right? Because you think about it, when you rotate it 120 degrees, the shape remains the same, or they look exactly the same. And the second type is reflection symmetry, which you can reflect across three different axes. The first axis is the perpendicular bisector of the bottom edge. The second one is the perpendicular bisector of the left edge. And the third one is the perpendicular bisector of the right edge. And by doing that, you can also think the shape of the object also doesn't change, and they look exactly the same, right? And the third one is, I call it kind of the silly symmetry, which is the identity symmetry. Basically, what you do is you basically do nothing to the object, because when you do nothing, it of course looks exactly the same, and it's called identity. And then once we have all these three kind of symmetries, we can try to compose these symmetries to get some interesting results. So for example, here's an example of composition of symmetries. So first, if we reflect the equilateral triangle across the perpendicular bisector of the left edge, then rotate it 120 degrees, then reflect the triangle you get across the perpendicular bisector of the right edge, and you can see that the resulting action is actually just rotate this triangle by 120 degrees clockwise. So what it means is that you can compose any of these symmetries to get another kind of symmetry that's in this six different symmetries, you know? So once you compose two different actions, you get another action that's in this set. And that's pretty interesting. So actually, that's how our concept of groups in abstract algebra arise. It's actually basically symmetries. So what is a group? Although you can just think about it as the different symmetries of different objects. It can be a general n-gon, it can be a cube, it can be any geometric object. But more generally, groups doesn't really have to be symmetries. It can also be something else. For example, we say that a real set with addition is also kind of a group. So what exactly is a group? So there are four axioms that the conditions for a group to define a group. So the group is a set equipped with a binary operation. So I believe most of you guys probably know what is a set. So a set is basically a collection of numbers or collection of objects. For example, I can call a set to be 1, 2, then it's 1 and 2 are elements in this set. Or we can say, yeah, it's basically a collection of numbers. And what is a binary operation? A binary operation is basically operations that takes two inputs and get one output. So for example, most common or the simplest binary operation example is addition or multiplication or division or subtraction. They're all binary operations. For example, I say 1 + 1 = 3. Oh, 1 + 1 = 2. Oh my God. Okay. So here, the addition is the binary operation, and the 1 and 1 are the two inputs, and the 2 is the output. Okay. So the first condition for a group is there exists identity, which here is basically if you compose two of the elements in this group, the result doesn't change. So there exists a G in the set G, exists an E in set G, such that E star, remember star is the binary operation we define. So E star G = G star E, which is equal to G for all G in this group. And the second one is the existence of inverse. It's a kind of element that undo that action. So for all G in this group, there exists a G prime such that G star G prime equals to the identity. So it's a operation that it's an element that undo. For example, here the G prime is an element that undo the action G does. Okay. And for the third one, it's called associativity. I believe most of the guys probably heard of this name since prep school. So basically what it says is you can change the order of operations. You can calculate, for example, here, G star bracket P star Q. So here you calculate P star Q first and get an output, and then calculate G star that output. But you can also do G star P first, then do this output star Q. And once you change this, the order of your calculation, the result doesn't change. And the final axiom or the final condition is this set is closed, which means that for any GOP, GMP in this group, G star P, which is also in G. So no matter which two elements you choose, if you compose them or you can put them into the binary operation, the result is also in this G. So the set is closed. And yeah, so I want to talk about, wait a second, why talk about symmetries here? Because if you think about it, symmetries, the symmetry of equilateral triangle, it's a very common example of a group. So, and you can check it out. It follows all four conditions. For example, existence or identity is just the identity symmetry. And the existence of the inverse, for example, if you do rotate this triangle by 120 degrees clockwise, you can undo this action by rotate this triangle by 240 degrees clockwise. So the inverse also exists. And associativity, you can check it out. It also follows that. And as I said before, no matter which two symmetries you choose to compose, the result you get is also in these 6 symmetries. And actually, this symmetry of equilateral triangle has a name. It's called a dihedral group of 3. Okay. And once we get to groups, now we get to matrix. So here we only need to know about the square matrices, which is kind of sounds intimidating, but it's actually not that complicated. So what do I mean by square matrices? So what is a matrix? A matrix is so square matrix is the 2 by n matrix that you have n rows and n columns. So you have n square entries. And for each entry, you have basically you have n square entries. And if you have 2 square matrices, A and B, and we call Aij to be the entry that's on the ith row and j's column, and Bij similarly is the entry in B that's on the ith row and b's column. Then if we let C equals to A plus B and D equals to A times B, I'm going to show how you define addition and multiplication on these matrices. Okay, so here, if we do the addition of the matrix A plus B matrices, then the result C will also be a square matrix of an n by n matrix. So it has the same size as A and B, to say. And where the Cij, the entry in C that's in the ith row and j's column, it's simply the sum of the entries in A and B on the corresponding location. So you just plus these 2 entries together, basically. So here, for example, because I don't have LaTeX in like Google Slides, so I'm just going to I just like search up some pictures from online. But for example, here A is A, B, C, D, and B is E, F, G, H. And if we do C equals to A plus B, right? So the first entry of C, the entry that's on the first row and first column, is simply A plus E. So it's the sum of the entries that's in corresponding locations in A and B matrix. And also for example of entry that's on first row and second column, it's just B plus F. No, yeah, B plus F, because you just get a sum of the entries that's on the first row and second column in both in A and B. Okay. And the product of two matrices actually gets pretty complicated. So one way you think about this is the inner product of the i's row and in A and the j's column in B. So what does it mean? So here I'm also going to, for example, here, if we think about a two by two matrices. So where C equals to A times B, and A is A, B, C, D, and B is E, F, G, H. So the entry in C that's on the first row and first column is simply the inner product of A, B, and E, G. What I mean by that is the product of the entries that's in corresponding location in these two rows, kind of. So you take the first entry that's on the first row times the first entry in the first column in B plus the second entry in the first row in A times the second entry in the first column in B, and you add them together, which is AE plus BG, and that becomes the entry that's on the first row and first column. And if you let's say the entry that's on the first row and second column in C, how do you calculate is you take the i's row, which is the first row in A, and the j's column, which is the second column in B, which are AB and FH. You also do the inner product, which is A times F, because A and F are the first entries in the first row in A and the second column in B, and then plus B times H, because B and H are the second entries in the first row of A and the second column of B. And you do this generally, you get the product of matrices. And that's how we define multiplication in matrix. And here I also get another example of a 3 times 3 by 3 matrix. And how do you calculate it? For example, the first entry is 1 times 1 plus 2 times 2 plus 3 times 7, right? It's the inner product of the first row and the second and the first column. Okay. And now we finally get to representation theory. So what is a representation theory? So what is a representation basically? So if you think about it, it's actually how you assign matrices to the different elements in the group. So remember, group is algebraic structure we defined here, right? And you basically assign different matrices to the elements of group in a way that preserve the structure. So what do I mean by the structure of the group? So the structure of the group, for example, here, if you assign matrix A to element A in G, and group B and matrix B to the element B, small b in G, then if you do A star small b, and this element will map to the product of matrix A times matrix B. In that way, you kind of preserve some of the structure of this group in a kind of like a linear system. And if you want to get more technical, What is it? It's a homomorphism from a group to the n-dimensional general linear group. And it's okay, like the terminology doesn't really matter here, but in case someone is interested in it. And for example, and here is a picture. So you have a group G, right? And you have a group operation. And what it means by a morphism is basically a function that maps from the G to the vector space, which is the general linear group of n. And what does it mean by general linear group of n? Basically is the set of O n by n matrices, okay? And kind of the general linear group and the morphism here kind of preserves some of the structure of the G, group G. And still it sounds very confusing, right? So I'll give an example. So for example, if you want to represent D3, remember what is D3? D3 is the dihedral group of 3, which is here, the symmetries. So if you want to use the matrices to represent the symmetries of an equilateral triangle, how do we do that? It sounds pretty complicated, right? But actually not. So the first one is a trivial representation, which is you basically assign a 1-by-1 matrix. What I mean by 1-by-1 matrix is just a real number. Assign number 1 to every single element in D3. This is a silly representation because think about it, no matter what you compose, for example, you compose the, let's say the rotating it 120 degrees and then compose it with rotated 240 degrees. And the matrix that represent both of the kind of actions are 1, right? And if you do the product of these two matrices, which is 1 times 1, which is also 1, and the result of the composition of rotating 120 degrees and 240 degrees is simply rotated 360 degrees, which you have identity matrix, identity symmetry, which is corresponds to 1. So 1 times 1 equals to 1, basically. That's what trivial representation means. It simply uses the fact that 1 times 1 is always equal to 1. Okay, but the second one is the 4D representation. And honestly, though, it's pretty complicated. And I'm not going to get to how do you construct these representation because that's a long story. But if you, and here you see a table here. What does it mean? So what does it mean? Basically, you see the first column and first row, right? And the first row means the first element that's in D3 that you want to compose. And the first column is the second element that's in like a D3 that you want to compose. So basically, for example, you see this is 1 and this is A. So, and here, for example, A compose 1 is A because 1 here is the identity. So yeah, basically this tells you how basically the structure of this group. And if you observe it carefully, you see that A compose A is identity, B compose B is identity, C compose C is identity. So what it means is that if you do A and B or C for twice, you get identity, which means that it's just the 3 reflections, right? And for D and E, then it must be the rotations, the 2 rotations. And if you work it out, working with the multiplication of matrices, you can see that it's actually a valid representation. But yeah, you know, multiplication matrices is very time consuming, so I'm not going to show it right here. But yeah, and the third representation is simply taking the determinant of each matrix. And this is called a sign representation. So basically is because the determinant of matrix A times the determinant of matrix B equals to determinant of A times B matrix. And you don't have to know this, but what I mean here is notice that for any group, the representation is not unique. So you can have a variety of different representations in a variety of different dimensions. So yeah, so the thing is, why do we even need to care about these representations? Because it seems that it only makes things much more complicated, right? Because you basically are learning a weaker version of a group that preserves like even less structure than original one, right? But actually it's very, very useful. So I want to talk about here, why is it useful, especially in mathematics? Its first application in mathematics is actually the proof of Burnside's theorem, which says if G is a group, you don't have to know what does the theorem actually means, but in case someone is like some of you are interested in, if G is a group of order that has only two at most two prime factors for some prime numbers P and Q, then G is a solvable group, which simply means it's the sum of the extension of a abelian group or a commutative group, but you don't have to know that. And you know how long? So Burnside was originally opposed to like the creation representation theory. He described it as a useless field, but in fact, after like 10 years, he's actually a pioneer in the field of representation theory, and he proved his most famous theorem using representation theory. And it takes a long time to find a proof without using representation theory. If a mathematician wants to prove Burnside's theorem without like a representation theory knowledge or machinery, and it actually takes 70 years for mathematicians to use purely abstract algebra tools to prove this theorem. So I want to say is representation theory is very useful in mathematics and especially in algebra. And also, why is it useful is more, I want to let you think about an analogy. So why would you care about a tangent of a geometric object? So a tangent basically provides you a way to linear approximate a geometric object, right? So from that linear approximation, you kind of get some information about the original object. Same for the representation theory. It's a linear approximation of an algebraic object. So typically a group. So, and I want you to think about is, why would you need, it's a linear relation, right? It's a linear approximation. Why is linear good? Linear is always good. Why is that? Because if you think about it, when you're working with, for example, an equation of a line, the linear equation, it's very simple and very easy to work with. But once you get to quadratic, polynomial, things gets very complicated, right? So here you have actually a tool, the representation theory, that provides you to reduce kind of a polynomial function to a linear function that actually, although it might lose some information, but it's much easier to work with. And the second thing is, in representation theory, the geometric object that we are acting on doesn't really matter here. So what it matters is how the actions are structured. So what it means is that I also want to, let's get back to the symmetries of an equilateral triangle. So in representation theory, the equilateral triangle itself doesn't really matter. What matters is how these symmetries are structured. So in representation theory, the original object that you study the symmetry is become a kind of like a abstract thing to think about it. It's like what you more care about is the structure of the symmetries of itself, not only the shape of it, And it also provides another kind of like a cycle in math research. So once you encounter a hard problem using, for example, a hard algebraic problem, what you do is you first use representation theory to linearize the problem involving that kind of preserve like the structure. And then you using linear algebra to decompose these actions. And once you decompose these actions, you get back to the original problem, and it provides you new insight. And once you get new insight, you can have more ways to linearize the problem. Then you also decompose them, then you get more new insight. So it's a kind of like a benign cycle of math research, right? Okay, that's pretty much the preliminary of representation that you need to have a sense to kind of get to know the math field. And right now I want to share a very, very famous example of the use of representation theory in particle physics. And actually it's called the Eightfold Way. And why is it created? So because physicists discover a variety of new particles, but they have no idea why they exist and how to classify them into groups. So originally, physicists only know that, for example, there are protons, neutrons, and electrons. But in the 1950s, they began to see a lot more particles. That's very interesting. But what Murray Gell-Mann did is he used the Eightfold Way to classify these particles. And through this classification, he proposed the existence of quarks. And that's how we get to know the existence of like the more fundamental building blocks, which are quarks, that in the universe. And it was done in 1961. And 8 years after that, Murray Gell-Mann was awarded Nobel Prize in Physics for his creation of Eightfold Way. So what it actually does, so first of all, in particle physics, there are actually 6 different quarks, and there are 3 light quarks and 3 heavy quarks. And the 3 light ones is our focus right now is up, down, and strange. And what I mean by light and heavy, they're in terms of the mass of a proton. And the hadrons is another terminology we use. Is the particles formed by quarks binding together. For example, a neutron is made up of 2 down quarks and 1 up quark, and a proton is made up of 2 up quark and 1 down quark. And the third one is the strangeness. So strangeness, now we know, is a number of strange quarks in the hadron. But at that time, physicists have no idea about the existence of quarks. So it was a kind of created quantity because there were a group of particles that physicists are really confused with. They are very, very easy to, not like very easy, but like rather easy to produce, but they decay very slowly. That's called strange quarks. Oh no, they're called strange particles. And through that, they've kind of created a quantity strangeness that's a conservation law in their creation and in their decay. And after that, they kind of find that the strangeness is corresponded to the number of strange quarks in the hadron. And the third one is the fourth one is the flavor symmetry. This is very important because so how do we get to a flavor symmetry? Also, physicists don't know about flavor symmetry like before the creation of Eightfold Way. They realized that there exists this kind of symmetry, and then they proposed the existence of quarks. But what it means is that because different types of quarks, we have 6 types of quarks, right? And different types of quarks, they perform like the same way when they're in strong interaction force. So we kind of can't change a up quark to a down quark, and the strong interaction force between these quarks still remains the same. And we kind of can rotate this it's called flavor rotation. You can rotate the up quark to a down quark to up quark. And by changing this, we build up a relationship between different particles. And these particles kind of perform the same way under strong interaction force. And basically the favor symmetry says is the quarks are regarded the same in this symmetry. However, this symmetry is not accurate because up, down, and strange quarks, for example, have a variety of different properties. For example, the mass of strange quark is much more heavier than up quark and down quark, and the charges of up quark and down quark are different, and also they perform differently regarding the weak force. But still, it's a pretty good approximation, right? Because the weak force and the electromagnetic force in the subatomic level is actually very weak compared to the strong interaction force. Okay, so what Gell-Mann actually did is he classified the basic particles based on actually three quantities. There are strangeness, charge, and another quantity called isospin. But the isospin is very, very complicated to explain. So I'm going to talk about mainly strangeness and charge in this kind of like classification. So you can see on the first row, which are neutron and proton N and P, they have strangeness of 0. In the second row, which is sigma minus, sigma 0, lambda, sigma plus, they have strangeness -1. And in the last row, which are psi minus and psi 0, they have strangeness of -2. So he arranged it in a way that's in the same row, the strangeness of the particles are the same. And also what he did is he also arranged this in terms of charges. So it's in a tilted row, right? So what I mean by tilted row, for example, a proton and the sigma plus, they have a charge of +1, right? And in the second tilted row, which are neutron, sigma minus, sigma 0, and lambda and psi 0, they don't have any charge. And a third row, which are sigma minus and psi minus, they have charge -1. In this way, Gell-Mann arranged them like into this, we call it an octet, which is basically a hexagon and 2 dots at the middle. And this actually corresponds to the 8-dimensional representation of the group SU3. And as I talk about, SU3 is called the special unitary group, and it's a very important grouping, especially in the use of modern physics. Yeah, and why is it 8-dimensional? And see that there are 8 particles, and each particle kind of corresponds to a dimension in the representation of SU3. And this group is and all the physicists are really familiar with this group. And once he discovered that, you see that, oh, this is the representation of a group called SU3. So what does it mean? So here I'm going to do this is what he get, like from the representation, right? He got an algebra for flavors. What does it mean by flavor? Flavor is basically the type of different particles. So he has a 3D vector space. What I mean by 3D vector space, you can think about, for example, here the up quark is 1,1,1,0,0, which is the x-axis. Down quark is 0,1,0, which is the y-axis. And the strange quark is 0,0,1, is the z-axis. So you have a 3D coordinate system, kind of. And a flavor rotation is when a vector multiply the element of SU3. So it's a action of the group. So what is the SU3? It's a unitary group of 3 times 3 matrices of determinant 1. And what I mean by unitary group is that the conjugate in terms someone is, although it's like pretty advanced linear algebra and it's kind of complicated to explain, but if you're interested in, the unitary group is the group that the matrix is the for matrix in the unitary group, it's complex. No, wait a second. Yeah, conjugate transpose is also its inverse matrix, and yeah, and if you multiply XYZ, you by a matrix A, you map the XYZ, which represent a particle that has X up quarks, Y down quarks, and Z strange quarks to another particle. And for example, here, if you say A is 0, 1, 0, negative 0, 0, 0, 0, 1, then a matrix A actually exchanges every up quark to a down quark and a down quark to up quark. So what it means, for example, proton, we know it consists of 2 up quarks and 1 down quark, right? So the vector is 2, 1, 0. And a neutron is consisting of 2 down quarks and 1 up quark, right? So it's 1, 2, 0. So you see that by multiplying the matrix A, you kind of map the proton to a neutron, which you have 2, 1, 0 becomes 1, 2, 0 if you're doing it by matrix multiplication. And this way, we can kind of rotate the different particles. For example, here we rotate the up quark and down quark, and we kind of build a relationship between the proton and a neutron. And once he observed that it's a representation of SU3, he sees that because SU3, each of the quark kind of represent an axis. So he instantly knows that maybe there is 3 more fundamental building blocks in the universe that makes up protons, neutrons, and other other particles, because it's a 3-dimensional kind of like 3-dimensional vector space with each axis represent a quark, right? Now we know it's quark, but at that time he doesn't know, but he knows it's something that's more fundamental and more profound. So that's how he actually come up with the idea of proposing quarks, proposing quark model. That's pretty interesting, right? And finally, actually representation theory has another major application in the real world. That is the chemists, they actually also use representation theory to study the symmetry of molecules. So here you see, I have 2 molecules and study the symmetric axis of different molecules. And they will actually have the different representations of these groups on like a theoretical chemistry textbook. And why is that? Because the different symmetries of a molecule will actually significantly influence chemical properties, how it will connect kind of like with other molecules during chemical reaction and how active it is. Yeah, and that's basically my presentation, and hope you are started to be interested in representation theory and modern physics.
Yeah. Okay, thank you, Alex, for your amazing lecture on group theory and their symmetries, as well as the representation theory and the quarks.